I would like to reiterate the importance of understanding the scale. So I made a little side note, and the number 1 to 10 scale means you are scaling down. So the part itself is 10 times larger than the drawing. So the number, the first number in the scale, is always the drawing, is what you see in the draft. When it says 10 to 1, you are scaling up. So it's slightly different from scaling down. In some cases, the part is so small that you have to make it much, much larger just to show the details and apply the dimensions onto the part. So scaling down 1 to 10, scaling up is 10 to 1. Reading industrial drawings. In your practice, you will see detailed drawings as well. And it's basically a technical representation of one single part of a machine. So a machine will very likely come with many, many pages of different drawings, and they will all have one single part. That's what it means, a detailed drawing. A detailed drawing will have all the elements of a regular drawing. It will have all dimensions fit in, it will have tolerances, and it will have a proper title block. Basically, it's a description of one single part of a machine. Assembly drawing, it shows various pieces of equipment, how they fit together. I don't believe you have this drawing in our Millwright manual, but I just found this assembly drawing as a good example of what assembly drawing does. And when I look at the cross-sectional view in AA, so along A lines here, I can understand how all the parts fit together, and actually I can understand how to disassemble it. So in this case, if I pull the center out, which is jammed into the spindle by some kind of tight fit. Once I pull the spindle out, then I can back out this nut number 8. So it tells me what to back out, lock nut. Then I can remove the handle, which is number 5, and I can cross-reference to the part number. And then I will be able to undo the cap, which will allow me to slide the rest of the machine out. So this is the purpose of the assembly drawing. And as you see, this particular assembly drawing has a bill of material. You will hear BOM or BOM. So that means a bill of material. And according to these drawings, all the materials are listed in this block down here. So again, that bill of material is right above the title block. So title block, in this case, it has a drawing number, the name, the what kind of projection, what kind of orthographic projection, first or third angle. It has a scale it's drawn to. It has a date when it's made, who drew the draft, and the name of the company. In this case, it's some college. Now, this one comes from our Millwright manual. So on page 3-28, that's another example of assembly drawing, and it's a hook. So out of this assembly drawing, I can say that the bill of material is right here. And referring to the bill of material, I can understand how to disassemble this part. So in this case, I have a nut, number 7. So if I cross-reference to a nut, it's like a lock nut, number 7, and there's a locking pin in number 8. So that nut is being held by a locking pin to the hook so it doesn't fall out. And also there is a cable that is running through this sprocket right here. And I can see in cross-sectional view that this material is steel, so mild steel, the same as this U bracket in here as well. So these two parts are made of the same material, of very likely cast steel. And if I look close enough, I can see there's some different material as well. So number 5, I would go to bill of material and cross-reference to number 5, and it actually tells me it's some kind of bushing. So the bushing itself is made of a different material, which is brass or bronze. Okay, so now we're moving on to schematics, piping drawings, and symbols. Schematic diagrams, they facilitate the tracing of hydraulics, pneumatics, electrical lines or components, and it actually doesn't show the actual sizes, shapes, or locations of those components. All it does is just assist you with troubleshooting. And also it assists you with disassembly and reassembly again. So in this example, I'm looking at the hydraulic system diagram, and I don't know what kind of hoses are between the pump. This is the pump. I don't know what kind of hoses between the valves right here, or between the cylinders. There might be pipes, tubing, for example, instead of hoses. I have no idea. And in case of schematic diagrams, I don't need to know this. This only to help me with troubleshooting it. So I can see that the pump is being driven by a motor. There's a filter. If I understand all the symbols, I can see the pressure relief valve. There's a directional control valve, and I see 2 cylinders, and I can look at the symbol for the directional control valve, and I can understand, I can read what goes first. And it looks like in this example is a cylinder that presses on the side of this storage, and once the pressure is reached on this clamp cylinder, then the press cylinder will come down. So all it does, it just tells me how the system operates for troubleshooting purposes. This is the pneumatic system, which is very similar symbols to hydraulic symbols. And as you know, a pneumatic system uses air to move components, while hydraulic system uses pressurized oil for transmitting work. Another schematic is the electrical schematic, and exactly the same purpose as the hydraulic schematic, just tells me how the thing works. So there's a switch. When I switch it on and the current flows through the stop button, normally closed stop button, then I can push the start button to start the motor, coil of the motor. And then when that motor starts, there's an overload that constantly closed, and therefore I have a path of current going to another leg, and I have the circuit completed. So when the circuit is completed from one leg to another, then the current starts flowing and the system is closed. So these schematics are usually used for troubleshooting, and it just tells you a general idea how this system works, either electrical, hydraulic, or pneumatic. Pipe drawings are slightly different from schematics because they may be located spatially. Spatially, what it means, it's basically isometric representation of the piping throughout the plant or throughout the machine. And there are 2 ways to draw piping lines, either single line or double line pipe diagram. So you may see isometric single line, and that isometric single line is represented in orthographic projection. So again, this is just basic orthographic projection, looking from the top, looking from the front right here. So front, top, and again the side. For double line drawing, you will see something similar to this representation or the diagram. So double line, 1, 2 lines, make it almost pictorial representation of the lines. And this is again B and C are the single line representation of the piping diagram. So here's a good example of double line piping diagram, and it will tell me the purpose of every valve. What do the valves do? What does air unit do? And again, it assists with troubleshooting and assembly procedures. And last is symbols and abbreviations. And you will be dealing with three standards. First of all, it's the ISO. Second of all is the CSA. And the last one is ANSI. So those three organizations, they will be dictating different symbols that are used in hydraulics, pneumatics, and piping to make diagrams. So again, it's the ISO, International Standard Organization, Canadian Standards Association, and American National Standard Institute. Those three institutes, they make the symbols that could be read by anyone throughout the world. They're all consistent and they assist us with identifying components of different systems. And at the beginning, as the last exercise, I would like you to fill out questions 43 to 62 using Millwright Manual Chapter 3.